Hello guys and welcome back to the reaction zone. In today's lesson, we're going to look at coordinate covalent bonding. In a coordinate covalent bond, only one of the bonding atoms donates the electron pair for sharing between the two atoms. In other words, coordinate covalent bonding, also known as dative bonding, is a type of bonding in which the shared electron pair is donated by only one of the bonding atoms. The bonding atom that donates the electron pair for sharing is called a Lewis base. And the other bonding atom that accepts the electron pair is called a Lewis acid. So this means that a Lewis base is a substance that donates an electron pair in forming a coordinate covalent bond. And a Lewis acid is a substance that accepts an electron pair in forming a coordinate covalent bond. A coordinate covalent bond is usually represented by an arrow that points from the donor atom, that is the atom that donates the electron pair, to the acceptor atom, that is the atom that accepts the electron pair. The atom that accepts the electron pair usually has empty orbitals with which it accepts the electron pair. Examples of compounds that are formed by coordinate covalent bonding are as follows. The first one is ammonium ale, Na4+. In ammonium ale, ammonia forms a coordinate covalent bond with hydrogen ion. Hydrogen ion has an empty 1s orbital. It does not have any electron to donate for sharing. Ammonia, on the other hand, has a lone pair of electrons on the nitrogen atom. So what happens in the formation of Na4+ is that ammonia donates its lone pair electron for sharing with hydrogen ion, leading to the formation of ammonium ion. And this arrow here indicates that the nitrogen of ammonia is donating the electron pair for sharing with hydrogen ion. The second example is the formation of carbon-2 oxide. In forming carbon-2 oxide, the two atoms that are involved, that is carbon and oxygen, each donates 2 electrons for sharing. So, the carbon atom donates 2 electrons, the oxygen atom donates 2 electrons for sharing. And that leads to the formation of 2 ordinary covalent bonds. The first 2 bonds here are ordinary covalent bonds that are formed as a result of the 2 electrons that each of the atoms involved donate for sharing. However, in addition to the 2 electrons that each of these atoms donates for sharing, the oxygen atom also donates a lone pair of electrons to the carbon atom. And that is indicated by this arrow that is pointing from oxygen towards carbon. So, there are 3 bonds between the carbon and oxygen atom in carbon-2 oxide. Of the 3 bonds, 2 of them are ordinary covalent bonds, and the third one is a coordinate covalent bond. So this tells us that apart from the 2 electrons each donated by carbon and oxygen atoms in forming the ordinary covalent bonds, that oxygen donates one of its lone pair of electrons to carbon. And that leads to the formation of a coordinate covalent bond, which is shown by this arrow pointing from oxygen to carbon. The third compound we're looking at is the formation of this coordination compound, hexacyanoferrate 3A. and 6, 3 minus. Hexacyanoferrite in forming this coordination compound, cyanide ion donates an electron pair to the central metal ion, which is ion 3 plus. In forming hexacyanoferrite ion, 6 cyanide ions will donate an electron pair each to the central metal ion, which is ion 3 plus, leading to the formation of this structure here. This structure here is hexacyanoferrite ion. What happens in this case is that the cyanide ions are ligands that donate electron pair for forming a coordination compound. They donate an electron pair each to the central metal ion, which is ion 3 plus. So let us look at how this happens in a bit of detail. The electronic configuration for Fe3 plus is argon 3d5 4s0. So in the d orbital, which is dxy, dyz, dxz, dz squared, dx squared, y squared. In the d orbital, there are 5 electrons, and the 5 electrons are unpaired. For the central metal ion, which is ion 3 plus, to accept 6 lone pair electrons from 6 cyanide ions, it is going to require 6 vacant orbitals. The Fe3 plus ion already has a vacant 4s orbital as well as 3 vacant 4p orbitals. However, it needs 6 vacant orbitals to be able to accept 6 lone pair of electrons from 6 cyanide ions. So what happens? The cyanide ion, Cn- is a strong ligand. So what happens is that it makes the electrons in the d orbitals to pair up. So the electron from the 3dz squared orbital comes here. The one from the 3dx squared y squared comes here. And then what will happen is that it will lead to the creation of 2 empty 3d orbitals. The next thing that is going to happen is that there will be a hybridization between these 2 3d orbitals and this 4s orbital, as well as these 3 4p orbitals. In other words, the kind of hybridization that will take place between the d orbitals, the s orbital, and the p orbitals is called d2sp3 hybridization. So after the electrons in the d orbital have paired up, leading to the creation of 2 vacant 3d orbitals, the 3d orbitals as well as the 4s orbital as well as the 3 4p orbitals will undergo d2sp3 hybridization. After this, Fe3 plus now has 6 vacant orbitals to receive the 6 lone pair of electrons from the 6 cyanide ions, leading to the formation of this coordination compound. Because if you remember at the beginning of this class, I said clearly that the electron pair acceptor must have empty orbitals to accept the shared electron pair. So, the electrons that will be donated by the ligands for sharing with the central metal atom Fe3+ will be in these vacant orbitals, these 6 vacant orbitals. So what that means is that each of the 6 cyanide atoms will donate an electron pair to Fe3+, leading to the formation of a coordinate covalent bond between each cyanide atom and Fe3+. And the structure that results is the coordination compound hexacyanopherin-3-atom. I want to believe that this explanation of coordinate covalent bonding is clear. Thank you very much for viewing, and see you in the next lesson.